Good morning. Today we will quickly revise the one component system water. Many questions were based on phase rule, especially water system only. Okay, now we will quickly revise what is phase diagram. Once you draw the phase diagram, you explain the phase diagram, and you will have triple point, that is very important, and we will solve few problems asked in GATE, CSI or JAM using the Clausius Clapeyron equation. Okay, now let us first see water. Water, there are two variables for water. There are two variables required to define the one common water. You define the system, equilibrium system. There are two variables. So, a plot of pressure versus temperature. A plot of pressure versus temperature will give you a phase diagram. Will give you a phase diagram on the effect of temperature, effect of varying temperature with respect to pressure on liquid waters, on water system will give this phase diagram. Okay, in water there are three phases: ice, liquid, vapor. How many phases are present in water? There are three phases. Therefore, there are three equilibria. Liquid is in, for example, you see there are three curves. There are three equilibria, liquid. So there are three curves: OA curve, OA curve. Liquid is in equilibrium with vapor, and OB curve. This is OB curve. Ice is in equilibrium with the vapor, and another OC curve. Ice is in equilibrium with the solid, is in equilibrium with the liquid. Okay, so the curve one OA is called the vapor pressure curve of water, and the curve OB is called the sublimation curve, and the curve OC is called the fusion curve or melting curve. There is another curve called OA dash. OA prime. This is called metastable OA. This is called metastable equilibrium curve. OA prime is called the metastable equilibrium curve. This state, liquid is in equilibrium with the vapor. This is a supercooled liquid. Actually, metastable equilibrium is supercooled liquid. For example, when water is cooled suddenly, below its freezing point, then it will be in liquid state, but it is not actually below freezing point. It should be ice. It should be frozen into ice. But because we suddenly cool the water system, therefore it is called a supercooled liquid. In the supercooled liquid, ice is not formed, therefore liquid is in equilibrium with the vapor. It is very unstable. On adding a piece of ice crystal, it will immediately freeze to give ice. Okay, so these three curves are stable equilibrium. This is unstable equilibrium. Okay, now let us see important one, triple point. What is triple point? The three curves OA, OC and OB meet at a point called a triple point. At triple point, the three phases coexist. All the three phases are existing. Okay, liquid phase, solid phase and water phase. Okay, at the triple point, the temperature is, for example, the temperature is 0.0075 degrees Celsius, and the corresponding vapor pressure is 4.58 millimeter mercury. By applying the phase rule, F equal to C minus T plus 2, we are seeing earlier, it is equal to 0. The degree of freedom is equal to 0. If the degree of freedom is equal to 0, then it is called invariant point. Triple point is also called invariant point. Now, what will be the effect of heat? Suppose at triple point, you are heating. I am heating the system at triple point. At triple point, there is no change in temperature or pressure on heating. See, simple. On heating, there is no change in temperature or pressure because all the phases coexist. And by heating, the ice will start melting by absorbing the latent heat of fusion. Therefore, there is no change in temperature and pressure. Similarly, increasing pressure. for example, increase in pressure also, there is no change in temperature and the pressure because of as long as the three phases exist, Okay, now let us actually Clausius claimed the equilibria, for example, the physical equilibria or chemical equilibria are quantitatively expressed by Clausius Clapeyron equation dP by dt. We have seen in the previous class. This is the differential form. This is molar volume in gas phase. This is molar volume in liquid phase. Okay, so several problems will be asked based on these two equations. Okay, now let us solve two problems. I solved here one problem, another problem, two problems. The vapor pressure of water at 95 degrees Celsius is 634 millimeter. For example, at T1, 95 degrees Celsius, the vapor pressure is 634 millimeter pressure. What will be the vapor pressure at 100 degree T2? At 100 degree T2, I am increasing the temperature from 95 to 100. Now what will be the change in the vapor pressure? So P2. Therefore, the given data is T1 equal to 95 degrees Celsius, 95 plus 273. It is expressed, the temperature should always be expressed in Kelvin, and the P1 equal to 634 millimeter, because millimeter will get cancelled, so you can use the same unit. Okay, and next is T2 equal to 100 degrees Celsius, therefore 273 plus 100, 373 Kelvin. T2, that is what will be the vapor pressure, that is the question they have asked. Therefore, on substituting in the expression P2 by T1 634 millimeter, and heat of vaporization is given in the problem, it is in joule per mole. If it is calories per gram, then you need to convert to per mole. In the second problem I have shown. Okay, so 40593 joule per mole. I always put unit also, so that whether it is G3 it get cancelled. Okay, so joule R equal to 8.314 joule per Kelvin per mole, and T2 this will come here. T2 is 373. Okay, and the T1 is 368 divided by T1 into T2, 368 into 373. On substituting, if you calculate, you get 760 millimeter pressure, that is 1 atmospheric pressure. Okay, we will solve another problem.
Here, let us solve a problem based on Clausius Clapeyron equation. We have studied in phase rule. The specific volumes of ice and water at melting point 0 degrees Celsius are 1.0907 centimeter cube and 1.001 centimeter cube. What do you mean by specific volume? The volume occupied by 1 gram of ice. This is the volume occupied by 1 gram of ice. This is the volume occupied by 1 gram of water at 0 degree Celsius. What would be the change in melting point of ice per atmosphere increase of pressure? That is, you are increasing the pressure by 1 atmosphere. You are increasing the dP equal to 1. dP equal to 1. You are given the heat of fusion equal to 80 calories per gram. It is given in gram. You remember. Okay, we will see now what is the formula to be used, what are the given data, and we will try to solve this problem. So for solving this problem, the Clausius Clapeyron equation for equilibrium process, this is for physical equilibrium process. It can also be applied for chemical equilibrium process. According to Clausius Clapeyron equation, for ice in equilibrium with water, dP by dt equal to delta Hf heat of fusion divided by T Vl minus Vs. Okay. In the problem, the following data are given. For example, specific volume is given. It is now converted into molar volume. What is molar volume? 1 mole of water equal to 18 gram. Therefore, 1 gram, what is the volume? Specific volume 1.0907 per gram centimeter cube. Now into 18, that is 18 gram, 1 mole of water occupy, 1 mole of ice occupies this much volume. Therefore, 1 centimeter equal to 10 power minus 2 meter. Therefore, 1.0907 into 18 into 10 power minus 6, because 10 centimeter cube, 10 power minus 6 meter cube per mole. Similarly, for molar volume of water, specific volume, the volume occupied by 1 gram is given, 1 gram. Therefore, into 18 into meter cube in SI unit, meter cube per mole. Therefore, 10 power minus 6. And the heat of fusion is given 80 calories per gram. Now it is per gram. Therefore, into 18 for 1 mole. 1 mole of water is equal to 18 gram per mole. Therefore, you always put unit. Whether it will get cancelled, you always put unit. This is very, very important when you solve for competitive examination, etc. Okay, now into 1 calorie. Here 1 calorie equal to 4.184 joules per calories. In joules, in SI unit, all of them are converted into meter cube, joule per mole, etc. And even dP, increase in pressure. What is the change in pressure? 1 atmosphere. And what is asked is dt. They have asked the effect of increase of pressure on the melting point of ice. Okay, so 1 atmosphere equal to, in 101325 Newton per meter square. Therefore, on substituting the given data in the formula, I have inverted the Clausius Clapeyron equation. dP by dt is dt by dP, because we are going to calculate dt. So dt by dP, 1 atmosphere equal to 101325 Newton per meter square, equal to T, temperature, melting point of ice, 273 Kelvin, into you subtract VL minus VS. Okay, so ice in equilibrium with the water. Therefore, VL minus VS, it will be negative, divided by delta HF in joules per mole. And if you cancel 1 joule equal to 1 Newton into meter, so you will get dt equal to minus 0.0075 Kelvin. So for 1 atmospheric pressure increase in pressure, the melting point decreases. You see, dP by dt, in the theory we have seen dP by dt is negative. Therefore, the increase in pressure decreases the melting point, whereas the decrease in pressure will increase the melting point. Okay, so similar problems were asked in GATE, CSIR, etc. So please try to understand and solve the problem. Thank you very much.